I'm going to talk about exoplanets, and especially how can we find them and how can we study them, characterize them. And toward the end of my talk, I will discuss a little bit about habitability and signatures of life. One important thing about exoplanets, it's a very it's a rapidly growing field. It's fascinating. There are a lot of discoveries. It's also extremely frustrating when you're interested in exobiology, in astrobiology, because this is really, I think, what everybody has in mind when we talk about other planets around other stars. But it's really the most difficult part, and it's really very far in the future that we will be able to discuss the habitability and discuss really with data the presence or absence of life on the planet. So that's an example of that. If you look at this is of course an artist's view of a planetary system, or part of it, that was found about 1 year ago. It's called Kepler 186, and it has at least 5 planets. And I'm showing off a little bit here because our team in Bordeaux contributed in finding the outer planet here, which was the first planet that we're sure it's rocky because it's small, and its temperature is compatible with having liquid water. We don't know if there is any water on that. So you can see a lot of beautiful animation with clouds, continents. We really don't know what this planet is made of. And actually, if you do a Google search on the name of this planet, if I do a Google search on that, this is what I get. I get plenty of nice pictures about this planet. And if you're not in the field, you may think that actually we know a lot about this world. For the French person, you can see that you also get some evil twins. That, okay, if you're not French, you don't know who they are, but it's a long story, whatever. But the actual data we have on this planet, it's this, and there is no more than this. This is what make us believe that there is a planet the size of the Earth that has a temperature that may be compatible with water. So what you have here is the time, and it's the flux. It's a photometry. It's the amount of light we get from this star with the space telescope Kepler. And well, every 120 days there is a very, very slight dimming of this star, apparent dimming of this star, which with only one case you would not be able to see. But because we have 5 or 6 of those, we can fold the time with the period of this event and find it. And it's an Earth-sized planet with a period of 120 days. But this is all we know. From the depth of this transit, we can infer the radius of the planet, but that's about it, right? And I will talk more about it. But I want to make you feel the fact that between what we dream about exoplanets and between what we really work hard to get, there is a huge gap, and there will be decades before we can say something much more interesting than that on this type of planets. So, but still, we have made progress, and when we look at the sky and all the stars, we are not exactly in the same situation as someone like 2,000 years ago in the antiquity or the Renaissance later. We know a little bit more. But basically, when scientists have looked at the sky, and basically there were, I would say, 2 main ways of looking at the sky. One was to say, okay, every dot in this picture is a sun. And because the sun has planets like the Earth, all these dots in the sky, they have planets and they have life. And life is everywhere. And that's the plurality of worlds. By analogy of what you have on Earth, you say it's everywhere, and life is everywhere. So we know, and actually with the same arguments, we believe that there was life plenty. There was plenty of life in the solar system. Maybe people on Venus were bluer, and people on Mars was redder and bigger and taller. But the exploration of the solar system showed us that actually in the solar system there is only one place where we are sure there is life. It's Earth. So we don't know if it's this analogy, this projection is correct. But there was another one which was mainly supported by religions in the world, which was the Earth is unique. and there would be no life elsewhere. And of course, when you're a scientist, none of this view is something acceptable. It has to be something between. The real question is, what is the distribution of life in the universe? Are we going to find life once per galaxy or thousands of times per galaxy? It's a quantitative question, and what will be the variations of that? So first, when we say every point on this map is a sun, it's not true. It's a star, and all stars are not equal, are not the same. So if I take all the stars in a sphere around the sun of about 10 parsecs, I don't know if you're familiar with this unit, the parsec. It's 3.2 light year, and it's a typical distance between two stars in our galaxy. And the definition is that it's the distance from which the Sun-Earth distance is supported by an angle of 1 arcsecond. That's the parsec. So within 10 parsec, there are about 300 stars, and we astronomers, we tend to give letters to stars, which is completely arbitrary. There is a real continuum of stars, but the Sun would be in this column. It's a G star, and I would say it's in the massive part of the star. There are much more stars that are less massive. Basically, the M stars, which are stars with less than half the mass of the Sun, are the biggest part of the population. And so if you go towards the massive star, they live very short time. So basically, A star, they live a few hundred million years, while the M star, they live forever, basically. And the Sun lives for about 10 million years. These ones are brighter. They emit more in the visible UV, while these ones emit more in the infrared, in the red. And okay, so stars are quite different, and we will see that you don't find exactly the same type of planet around different types of stars. So when we want to, okay, that's the first thing. So now, do all stars and have planets? Well, what we would like to do would be to take pictures, to zoom on every star and to see what there's around. But it's very difficult. There are three major challenges when we want to do that. It's that the three problems are: the planet is faint, the planet is much fainter than its host star, and the planet is very close to its host star. So the fact that the planet is faint, it's a difficulty, but it's not an impossible obstacle. For instance, if you take here what is called a Hubble Deep Field, it's a very long exposure with the Hubble Space Telescope, where this exposure reveals very distant, very faint galaxies. And this dot, for instance, probably a very distant quasar or galaxy, but it's an Earth at 10 parsec would be brighter than that, or less faint. So we have the capability to see the light from a planet. But the light from a planet comes from its proximity from a star. So if you have an Earth in the middle of nowhere, it won't have this luminosity. It will be even fainter. It will be impossible to detect. So we need to find this, but very close to something like that. So what is the contrast between the planet and the star? And it's a lot. So I will describe what you have here, because you probably cannot read. What you have here is the wavelength. So here you have the visible, 1 micron, 10 micron. Here it's the infrared. And this is the contrast from 10 to the minus 9 to 10 to the minus 3. And the blue curve are for an Earth-sized planet, and the red curve for Jupiter-sized planet, and at different distances from the star, 1 AU being the distance between the Sun and the Earth. And so in the visible, this contrast is just given by the dilution factor, because it's just the light reflected by the planet. So it's constant with the wavelengths. And then at some points, the planet emits at its own wavelengths in the infrared, at its own temperature, and then the contrast increases. So for an Earth, in the visible, you have 10 to the minus 9 and 10 to the minus 6 in the mid-infrared. So it's the star is 1 billion to 1 million more brighter than the planet. Of course, if your planet is bigger, you get a better contrast, and if you get the planet closer, it's warmer and it reflects more light, so you increase the contrast. But if you put the planet very close, you have a problem. It's that you have to observe it with a telescope, which has a finite diameter, And so the telescope is going to diffract the light and produce this kind of pattern. So your planet will be hidden within the fringe of this pattern. And there is this law that gives you actually the angular separation that you can achieve with a telescope of a diameter d at the wavelength lambda, and it's given by that. So for instance, if you want to know the size of telescope that you need to resolve the planet at this distance, with this orbital distance from its star, at this wavelength, you get the size of the telescope that you need. So for instance, if you want to see an Earth around a sun, so this will be 1. So in order to find an Earth and a sun, you need to look quite far, at least more than 10 parsec. Okay, let's say 20, for instance. Let's say 20. And let's say that you observed at 0.5 micron in the visible. So you can do that with a telescope of 2 meters. But if it's a sun and an Earth, you need to achieve a contrast of 10 to the minus 9, which is by far not reachable. If you go to the infrared, you can see that if I go from 1 micron to 10 micron, I need 1 order of magnitude increase in the size of telescope. But I can look closer because there are much more. If I look around M stars, for instance, I can look much. Maybe within 7-8 parsecs, I may find some. But the separation will be closer. So you also have a problem, and in this case, you may need a telescope of 30 meters, for instance, which we don't have at the moment. So we have a problem because we need to take a picture. We need a bright planet far from a star, and this happens sometimes when you have a young system. When you have a young system and the planet just formed during the last millions of years, the planets are still very bright because they're hot from their formation. And in some cases, you can see that. So for instance, this system, around this star, you can see 4 giant planets, bigger than Jupiter, that are orbiting this star. And it's a very young system, so they are still very hot. They're more than 1,000 Kelvin in temperature, so you can see them. So when you see that with your telescope, of course, you will find a great candidate, but you have to be sure that this is not a distant galaxy or a distant quasar, that is just very near in the background from your star. So you look 6 months after that, and because of the parallax, if you've lost this object, well, they're not planets. If they're still there, well, they're probably gravitationally linked with the object. And then if you looked several years after, you will start to see for the innermost of this planet, you will start to see that they move along a Keplerian orbit around the star. So there are maybe 20 planets that have been observed this way, and it's a growing field, and there will be plenty of results with this technique, especially with a European instrument called SPHERE on the VLT, and with an American instrument called GPI, Gemini Planet Imager. So it's a golden age for this kind of technique, because when you get one of these detection, you can also make a spectrum of any of these points, and you can compare with models and try to understand what they're made of. Are they similar to Jupiter? Are they similar to? And it's even more interesting. You know that for Jupiter or Saturn, we have the problem that we don't access all the elements. For instance, oxygen is trapped inside because of the condensation of water. The upper atmosphere that we can observe is cold, and the water is not there. So we had to send a probe inside Jupiter in order to try to get the elemental abundance of oxygen. It was Galileo, and it didn't work well. But for Jupiter like that are hot, you have all the elements that are there: carbon, nitrogen, oxygen, and all the carrier of these elements, water, carbon monoxide, carbon dioxide, methane, they're there, and you can observe them. So there is something you can do with exoplanets that you cannot do in the solar system at the moment. Another example is a famous one. It's Beta Pictoris. It's a disk that we see in this configuration. So we are really in the same plane as the disk. And the disk was known for a long time, but then a planet was observed called Beta Pictoris b. And it was even possible, I will not go into the detail, it was even possible using high-resolution spectroscopy to measure the rotation of this planet, and it rotates just at Jupiter in 10 hours. And it's possible because of the geometry of this system that Beta Pictoris b will transit, maybe in 1 year, maybe in 2 years, will transit its star. It will be very difficult to observe. So these are for the direct methods, and this is about it at the moment. This is what we can do in terms of imaging exoplanets. So then we have to use indirect method to find them. And there is one that I will not detail here, but just say a few words. It's called gravitational lensing, and because gravitation is, it's very hot right now. And so it's a technique that is very promising, that has already given some interesting detection. It used the fact that if you're looking at very distant stars, for instance, stars in the center of the galaxy, like this one, you're looking at it, there is a chance that there is another star in between, about halfway the distance, that is crossing the line of sight. And because of general relativity, it will act as a lens and will make the light that you get from the distant star increase during days or even weeks. Okay, this is called microlensing. And if this star here has planets, it will produce additional peaks because of it's called the caustic, and if you associate different lenses, it will produce something like that. And it's very interesting because it's probing a part of the parameter space that other techniques don't. So it's very complicated to go from that to the properties of the system, but it's possible, and I think it's a very promising technique. But the techniques that have given most of the results are illustrated in this animation. So the first one is to measure the change, the motion of the star that is induced by the presence of a planet. So the planet is both the planet and the star are orbiting around the center of mass. Of course, the star is doing a much smaller orbit, but still it's observable. And the other technique that we will see is the fact that in some case we are lucky to be in the plane of the orbit of the planet, and so every orbital period we can see a transit of the planet in front of the star. That will be the second method. So let's go back to the motion of the star. The most, of course, obvious thing to think about was to try to measure accurately the position of the star to try to see this motion on the sky. And this was done first for binary stars, and this is an example. The brightest star in the sky is Sirius, and it has been known for a long time that it's actually a binary, although we could not see the secondary star because it's a white dwarf and it's very difficult to observe. But it was observed after decades and even nearly a century of observation, that actually the motion was not a straight uniform motion, but there was an oscillation around a center of mass, and so it was possible to deduce the presence of another object which was observed later by X-ray, for instance, X-ray imagery. So let's say we're looking at the sun. We are 10 parsecs away from the sun. We're looking at the sun, and we're waiting a long time, so tens of years, to see the orbital motion due to mainly Jupiter and a little bit of Saturn. These are the two main influences on the sun. And this is the kind of motion you would have to see. Right now, this is the kind of precision we can have at best on that. So you can see that it's not good enough. And for this reason, we have not yet detected any planet using this method called astrometry. But right now, there is a space mission working called Gaia, and Gaia is measuring the position of millions of stars with this type of accuracy. So we have to be patient. After the 5 years, terminal 5 years of mission of Gaia, we will discover a lot of analogs of Jupiter and Saturn, probably on slightly shorter period, because we cannot use Gaia for 10 years or 20 years. We can only use it for 5 years because it has some fuel. It has to point, so it has an exhaustible amount of fuel, so it won't last forever. It will last about 5 years. But still, it will be interesting to see basically Jupiters and Saturn at about 1 AU, 2 AU, 3 AU from the star. Okay, but so we are not very good right now at measuring accurately the position of stars, but we are very good at measuring their speed, their velocity, using spectroscopy and Doppler spectroscopy. So how we do that? But we take advantage of the fact that stars are, the spectrum of stars is full of transition lines from atoms, ions, a lot of species. So actually we can use if we make a spectrum, high resolution spectrum of a star, we can see how the position of this line change with time. So for instance, you imagine that you mix this spectrum with a reference that's on Earth. So you're adding something in the optics, something that has its own lines, and you're measuring the distance between the lines that are in your instrument with the lines from the star, and you're measuring the shift between that using thousands and thousands of lines. So you point your instrument to a star, and you measure the velocity, and you will do that at different time. The first thing you have to do, of course, is to remove the motion of the sun, the Earth around the sun, 30 kilometers per second. Fortunately, we model this motion very well, so we can suppress it. Some of the first planets to be found had a 1-year period. It was very doubtful, and usually it was because this motion was not removed properly. But when it is removed properly, you should find something that is fixed. So if you observed your star now and maybe in 2 days and then in 1 month and then in 6 months and then in 2 years, you should find about the same velocity. If you don't see any change, well, it means that at the accuracy of your instruments, you haven't found anything. But you may find some periodic change, and in this case, you have found the planet. And the first time this was achieved was for this star, 51 Peg. And the characteristics of this planet were amazing at that time, were not expected because it was a Jupiter mass planet with an orbit of 4 days. And so it was a very easy to find planet in case later. So this is the first exoplanets around main sequence stars. There were planets found around pulsars before, but I won't discuss that. This is at scale. So everything is at scale on this drawing. So radial velocity, so this method is called Doppler search or radial velocity, and you can also use it to see, well, you will see the eccentricity of the system because the speed is going to be much higher near the periastron than at apoastron, and in extreme cases like this one where you have an eccentricity of 0.93, which is amazing, you will have a very, very peculiar case. So in a case where you have several planets, for instance, this is one, there are 3 planets here, two periods are obvious, so there is one here, there is another one here, and if you would zoom here, you would see there is an even shorter period planets here. So it was the first multiple system found. Okay, then the other method is the transit. And the transit is when you have the chance to get one, it's very useful. But it's not very likely to happen. If you take an Earth around the Sun, oriented randomly in space, the probability to get a transit, well, it's given by the radius of the star divided by the distance between the star and the planet. So for an Earth, it's that. So you need to observe 200 systems that has a Sun and an Earth to see one that transits. So you see only the tip of the iceberg when doing that. But for hot Jupiters, like 51 Peg, the probability is 10%. So you will see much more of them. The depth of the transit, if you know the radius of the star that you get usually from models, in some cases for very nearby stars you can measure it directly with interferometry, but that's very rare that you can do that. So you get the radius of the planet. If you measure the Doppler shift, so the previous method, on a transiting system, you know the geometry and you can derive the mass of this planet. And of course, the periodicity gives you the orbital period, and the typical duration for a transit is hours. So this is well, you saw it was a transit that I simulated with a very simple code, and you get 2 curves here. The flat one is the one I get if I assume a uniform luminosity of the star, but actually in star you have the limb brightening, limb darkening. So the limbs, the borders of the disk are darker than the center, and this is because of that you have this type of shape. So basically with the transit you can also probe this limb darkening. So the very first transit that was observed with this telescope, a 10-centimeter telescope. It was in 1999. The star is HD 209458. It's one of the big shots in the exoplanet world. And so this is what you get with this type of telescope, and this is what you get when you point the Hubble Space Telescope on the same target. And of course, you get a very, very neat transit from such a telescope. Let's talk about the catalog of known exoplanets and what we can say from the population. So on the left, you have the planet mass as a function of the orbital period. And the color that we cannot see very well here is depends on the technique that was used. So because it's the mass that's given here, all these planets has been found by a technique that can give you the mass. So for instance, when transit is shown here, it means that, okay, transit was observed, but also the Doppler spectroscopy in order to get the mass. And we will see that later, but already on that, you can see the main population known of planets, which are the hot Jupiters, like 51 Peg, the Jupiters that are not exactly analogues of Jupiter because they are slightly closer to the star at slightly shorter periods, but basically they are giant planets. And there is a hole in between the two. So it means that when you find a giant planet, it's either stuck to its star or at least one astronomical unit away from it. And in between, they are very rare. And those are very rare. It's only about, but I will go on that later, it's only about 1% of the stars, but this is more abundant. And this population is really what was amazing, because we don't have that in the solar system. We don't have planet in the solar system that has a mass between the mass of the Earth and the mass of Neptune. There is a big gap. But this gap does not exist in the population of exoplanets. These are the most abundant planets in the universe, probably. These are the planets that are fairly near from the star, quite hot, and bigger than the Earth and smaller than Neptune. We call them super-Earths, which is really bad name because we really don't know what they are. So it's not the home planet of Superman. It's super-Earth. It just means that we don't know what it is. And if you add to that, so in this case, you have the radius as a function of the orbital period. So these are meant to, and what you get here are transiting planets, and in yellow, the ones that have been found with the space telescope Kepler. And you can see that Kepler found a huge amount of these hot super-Earths, and even some sub-Earth planets, some being the size of Mars. But these ones are very, very difficult to confirm as planets, because we have no other techniques to find them or to confirm them or to reject them. It's very difficult. So let's go back to this population. It's the same, but instead of having the period of the distance, I plotted as a function of the temperature, because the distance does not give you the temperature. It depends on the star. Same for the period. So in case of temperature, you can see that we are getting planets that are the same temperature as the Earth, but most of them are giants. But we start to get planets that are temperate and with the size of the Earth. So sorry, the color here gives you an idea of the eccentricity. So the black ones are circular orbits, and they are usually very close to the star. This is because tides are making the orbit, force the orbit to become circular. And you can see that if you are far enough from the star, eccentricity does about anything. And that's a peculiarity of the solar system. We have circular orbits. It's not the majority of systems. So that's again the transiting objects, so the one that mainly Kepler has found. So you have the radius as the temperature, and you can see that Kepler has found some objects that have the size of the Earth and the temperature of the Earth, some slightly bigger, but between two Earth radii and one Earth radii, this is still a rocky planet, or probably. So there are a lot of Earth analogs. One of the big success of Kepler, and that was completely unexpected, because you have to. So let's say that away from the solar system, and you're looking at the solar system, and you're close to the ecliptic. So let's say that you see transits of the Earth. Are you going to see transits of other planets? Well, most likely no, because there are mutual inclinations between the planets. They're not very big, but they are enough to prevent you from, let's say, seeing transits of Venus, the Earth, Jupiter. You will get one if you are super lucky and very, very peculiar orientation, and you may get two, but that's it. So it was not expected that Kepler would find multiple systems. Maybe in some cases 2 planets, but marginal. Actually, Kepler is finding a lot of those. Up to 6 planets in the same system. And the first that I show you at the beginning had 5 planets transiting the same stars. So it means that some of the systems are extremely coplanar. They are not excited a lot. They have 0 eccentricities, 0 mutual inclinations. They are super quiet. Even the solar systems looks very, very hot compared to that in terms of, thermodynamically, if you mean, excited. So they are dynamically very cold. It was very, very unexpected, and it's amazing. And the big interest also of that is that when you have only one planet transiting the star, when you have only one periodic transit, it's possible that it's not a planet, it's mimicked by a configuration of stars, especially if you have a binary star, eclipsing binary, in the background, diluted with the foreground star. You may think it's a planet. If you have the Doppler search, the Doppler survey to help you, then you may be able to know that it's not a planet. But for the small planets, the Doppler survey are not accurate enough to do that. So, but in the case of multiple systems, the number of configuration that can mimic that drops by orders of magnitude. And so you are fairly sure that these are planets. And even more than that, many of these systems are very compact. For instance, this one, Kepler 11, you have 5 planets inside the orbit of Mercury, 6 inside the orbit of Venus. And these planets are between 2 and 14 Earth masses. So there is a lot of mass in a very small volume. And these planets, they interact together. So the orbits are not exactly Keplerian. And sometimes the transits of one planet comes a little bit in advance. Sometimes it comes a little bit delayed. And by modeling that with n-body simulation, you can constrain the masses of these planets. So in this system, the Kepler 11 systems, you can put error bars and you can put values on the masses of this planet because you can see the interactions of the planet together. So you know that these are planets for sure. And this is the example of the systems we've been working on, Kepler 186. So this is what happens, and you're looking, so the Earth is in this direction, and you get transits all the time. And we wanted to try to get something that was super exciting for us. There was not much science to do with it, but we calculated that last year at some point there was a transit of 3 planets at the same time, maybe 4. And we wanted to observe that with Hubble, but it was very difficult. And we have no very big argument except that that's super cool to observe. You know, there was not much science. Seemed enough for us, but these guys, when they give you a Hubble space telescope, they want to have added value in science. We didn't understand. We didn't get the time on that. But this is an interesting system, and the outer planet lies inside what we call the habitable zone. I will discuss that later. So it's an Earth-like planet around an M star, so a faint red dwarf. But it's possible that this planet has water. And it's interesting because this planet is in the outer part of the habitable zone, and that's good because contrary to the Sun, M stars have a luminosity that decreases with time. The Sun has a luminosity that increases with time. So basically, the Earth is going to be kicked out of the habitable zone from inside. So in 1 billion years, we are going to change into a Venus-like planet. In this case, the problem is that it was the contrary. When you find the planet in the habitable zone, in the past, it was very hot, and it may have lost its water to space. So it's good to find a planet in the outer part of the habitable zone, because in the past it was maybe here, but it was not there. So it's something to take into account. But again, there are a lot of imprecision, and the parameters on these planets and stars are not very well determined. And this is actually a work of Anthony. Is he right or not? Yeah, so Anthony Caldas, he estimated actually the among other things, the amount of light received by this planet in Earth insolation. So one would be the insolation of the Earth, and you can see that there is quite a big spread. And the reason for that is that we don't know the star very well. It's a distant star. It's not well characterized. So among the weird objects that they're weird for scientists, but not for filmmakers or science fiction authors, there are circumbinary planets, so planets that are orbiting not a single star, but a double star. So the first that has been found was Kepler 16b, and it was around a Sun-like star and a small M dwarf, so very similar to this double sunset or sunrise in Star Wars. And there are other ones that are all here. So Kepler 16 here. So the two red circles are the orbits of the stars, and the blue are the orbits of the planet, or the planets. Could be several ones. And you can, there is a region around these two stars that are unstable for planets. You cannot have an orbit stable there. And if you put all these plots together and look at the instability zone, well, it works well. We do not find planets inside this instability zone, which means that, okay, some things work. And you can have the other configuration when you have a wide binary star. You have wide binary stars and one or two of the, actually there is a case where we believe that, and it's very difficult to be sure, we think that actually both stars have planets. And there are about 70 systems known like that, but only 5 with a separation between those two stars that is less than 50 AU. So I don't know if you know, but the closest stellar system from the Sun is Alpha Centauri. It has 2 Sun-like stars plus a very distant M stars. And there was an announcement a couple of years ago that one of the 2 Sun-like stars had a terrestrial planet, Earth-sized terrestrial planet with a 1-day period, very hot one. But it seems that it's no longer there. I mean, they've been proven wrong. But it would be very interesting to find, this type of systems, but with 2 stars that are, I would say, closer than the size of our solar system, for instance. So about the frequency, the abundances of planets around stars, we have constraints on that. These constraints are now getting better, and we can have them from different techniques. So let's start with the big planets. So for instance, we can have constraints from Doppler spectroscopy. So hot planets, so with less than 10 days of period and bigger than 30 times the mass of the Earth, about 1% of stars have a planet like that. If you increase the period and look at bigger planets, so to give you an example, this is a little bit more than the size of Saturn, but it's 3 times less than the mass of Jupiter, then you're getting close to 10%. Actually, the global frequency of giant planets is above 15%. It could be bigger, it could be larger, but it's not going to be 20 or it's not going to be 30 or 40. Well, but Gaia will provide a lot of constraint on that. Okay, so hot Jupiter are about less than 1%, and otherwise 15% for giants. What's this? Okay, these are Earth-like planets, you see, about the size of the Earth. Hot ones, because these are FGK stars, so Sun-like stars, and with a period of less than 85 days, so from, I would say, temperate to very hot. 16% of stars have planets in this very short range of radius. If you go from 1 to 2, you go up to 26. And actually, if you go from 0.8 to, let's say, so if you go to 0.8 to 2, you have to add these two numbers, so it would be 36. And in planets in general, so if you go from 0.8 to 20 times the radius of the Earth, you have to add that, and that would be 70%. So in terms of planets, whatever they are, the majority of stars have planets. And we don't see the smallest ones. So we have a lot of arguments to believe, based on planet formation theories, that smaller planets are more numerous than bigger ones. So actually, it should be very close to 1, the probability for a simple planet. Actually, for M stars, in this range of radius, so between half and 55% bigger than the Earth, each M star has in average more than 1 terrestrial planet. So it's very, very common. And now if you're looking at Earth-like planets with about the same temperature as the Earth, so planets, terrestrial planets in the habitable zone, it's very difficult to get numbers because there are very few detections, and actually it's mainly for M stars that we have detection. For the other one, the error bars are huge. But for M stars, the numbers can be, okay, you can see the error bars. It's between 30 and about 100%. So these numbers are still very inaccurate, but they show big numbers, which is important. There is something interesting in the distribution of mass. So what you have here is the mass. It's the minimum mass, so the mass that is deduced from Doppler search. So it includes non-transiting planets. So the purple lines is for the planets with less than 50 Earth masses, and the green one is for bigger planets. And actually, so these are disconnected. So you can see that there is a hole between. So the distribution has two peaks. One that is around 10 Earth masses, and this is a biased sample. There is no correction. So actually, the fact that there is a decrease between these, between 10 and 1, it's just because it's more difficult to find a 1 Earth mass planet than a 10 Earth mass. But this is real, because here there is no bias. So it's probably the change from small planets to giants. Once you start to become a giant, it's probably you go all the way to Jupiter or Saturn. You don't stop in between. But it means that we used to believe that there was a dichotomy between terrestrial planets and then the giants in the solar system. So the icy giants and the giants, the gaseous giants, Jupiter, Saturn, Neptune, Uranus. But actually what we see is that the dichotomy is between the icy giants and the giants. Between Neptune and Uranus and the Earth, in the sample of exoplanets, there is no distinction, there is continuum. There is no change of, you see, no change of distribution. So, but there is a big change of distribution between the Neptunes and the Jupiters. Another interesting thing is if you look at the distribution of eccentricities, especially for the giants, you can see that, of course, there are more giants on circular. There are giants on circular orbits, but actually the majority has eccentricity that are bigger than those of the giants in the solar system. So we can use the distribution, for instance, to ask ourselves a question. We cannot say right now, is the Earth rare or common? We cannot give you an answer to that. But we can think about how common is the solar system based on that. So based on the properties that we know. So first, we know that the Sun does not have hot super-Earth. So it's about 50-50, probably 60-40. We are in a minority, but a small minority here. We have giant planets, so it's about 10% of 10-15%. We cannot actually combine these two, because usually planet that has giant planets, they don't have hot super-Earth. So I cannot multiply these two numbers. And we kind of understand why. Probably the formation of hot super-Earth implies that you don't have giant planets. So let's take the giant planets, 10% of the systems. And let's say that the sun is about 10% of stars. So we have 10%, 10%. Then there is the criterion on the eccentricity of the giants. we have circular giants, so it's about also 10%. So you multiply that, and you get, well, 0.1% of the stars. That it's an upper limit on the abundance of solar systems in the galaxy, something that you can call solar system based on these criteria. Well, that's still a lot of stars in the galaxy. It's well, it's less than 200 million, but okay. It's about it's the only kind of calculation we can do right now. But it's interesting that we are not the majority of the systems. Not all systems have the architecture of the solar system. So I've reached half of my talk, not in 45 minutes, but in 50. It's not bad. So English is more compact than French, actually. So how far can we look in our galaxy to explore the population of planets? So it depends on the technique. With Doppler searches, we need a lot of flux, so we can do high-resolution spectroscopy. So it's really the most nearby stars, so within tens of parsecs. With the transit searches, we need to look at many stars at the same time. So we need to look at a field, a very dense field of stars. This is what Kepler did. And because of that, it looks at stars that are more distant than Doppler searches. It's more typically, it's hundreds of parsecs. And it's a problem because it's difficult to get a confirmation or a characterization by other techniques because the Kepler stars are very far away. And this is why the European Space Agency selected Plato to do that again, but on the whole sky and focusing on the brightest stars. And then there is the microlensing, and the microlensing is probing even farther away, typically close to 1,000. Okay, when you have a planet that transits, you can get information on the composition of the atmosphere by looking at the depth of the transit at different wavelengths. So basically, if your planet is just a big sphere, solid sphere with no atmosphere, you can look at the transit in UV, in visible, in infrared. You will always get the same depth. But if you have an atmosphere that is more or less transparent in the UV, in the visible, in the infrared, depending on its molecular composition or maybe clouds, then you will get different depth. And this, if you plot the depth or the apparent radius of the planet as a function of wavelengths, then you have a kind of spectrum that is the spectrum of the limbs. And this is by this way that we detected water vapor, carbon monoxide, methane, for instance. Another way is to look at the eclipse. The eclipse is when the planet is hidden by the star. So when this happens, you're losing the light from the planet. So if you measure after and during the eclipse, the difference is the light from the planet. So if you're observing in the visible, it's the light reflected by the planet, and because you know the radius from the transit, you can get the albedo, so the reflecting power of the planet. But more interesting, if it's in the infrared, then you get the emission of the planet. So you get an emission spectrum, just exactly as if you would do that on an isolated object. You can get an emission spectrum of the planet and compare, just like for young hot Jupiters observed directly imaged, you can do emission spectroscopy. And then when you do that, you can also look at the emission of the planet along the whole orbital motion, because at the moment of the eclipse, the planet is showing us its day side. But when it gets close to the transit, it's showing the night side. And so you can look at the variation of the light from the planet. In the visible, it gives you just the phase, like for Venus, but in infrared, it gives you the difference in temperature between the night and the day. And the fact that the moment where the maximum of the emission occurs can give you the strength of the circulation in the atmosphere. For this has been observed. And actually, in our team in Bordeaux, we're looking mainly on this aspect. So, I don't know, it's, as we say in French, it's acte manqué. I removed that from my talk, I don't know. But I have the excuse that yesterday there was a big announcement on gravitational waves, and I got a little bit distracted from my talk. Okay, let's go on the fact that, okay, the idea is that on Earth, we have a big flag that can be seen across the galaxy, that there is something odd going on our planet. So if someone is getting a spectrum of our planet, either in reflected light or in infrared. And let's say that this distant observer is observing the three terrestrial planets, the main three terrestrial planets in the solar system, so Mars, Venus, and the Earth. You will see a planet, well, with some atmosphere of CO2. They will know that there's not a lot, because actually when Mars is showing the night side, all this infrared emission it's disappearing because the night side is very cold. So they will say, okay, there will no thermal inertia on this object. It has a very tenuous atmosphere. Then they will look at Venus and they will see, okay, this planet has an emission that does not move at all. It's completely stable, and while we can see a lot of CO2 actually, we can see even hot bands of CO2. So there is a lot of pressure of CO2. But basically nothing very interesting. But if we look at the Earth, okay, we see the CO2 all right. We see some water vapor. It's interesting. It has the right temperature to have this vapor in equilibrium with liquid water maybe. And it has some oxygen-rich atmosphere and an ozone layer. And if this observer has a very good instrument, it can also see that there is some methane in the atmosphere, which is kind of weird in an oxygen-rich atmosphere. It would not last long unless there is a very strong of both gases in the atmosphere. So we know now, because we live here, that this is produced by life. I mean, on Earth. The oxygen is produced by oxygenic photosynthesis, and ozone is a byproduct of oxygen due to photolysis of oxygen. And methane is also produced by life. So it's interesting because we have organisms that change the whole properties of our planet as observed from a distant location. And this is also true. So I told you that you can also get a spectrum from a transiting planet. So that would be a transmission spectrum of the Earth, so from visible to near infrared. So you need to be able to measure, it's like being able to make the difference between a planet of the size of the Earth and a planet of the size of the Earth plus 20 kilometers, which is very difficult. It's about 1 ppm in photometry. And you have a problem also with that, which is the refraction by the atmosphere that hides you the lower part of the atmosphere, but you would still see the oxygen. So, but the main point is that it's not all life that is producing that. It's actually the reason why there is something to see in our planet, something peculiar to see. It's because at some point in Earth's history, life invented that. Life invented a way to use the light from the star, from the sun. It invented it invented photosynthesis, and then oxygenic photosynthesis, which is a particular way of doing photosynthesis, and it's super complicated. I mean, for me, atmospheres and exoplanets are really simple compared to that. It's, I don't know, like a nuclear plant, more complicated. So, but whatever, I'm not a biologist, but this allowed life to do this kind of reaction. So it allowed light to use light to break the water molecules, and then to use the hydrogen to reduce the carbon from CO2 and to produce sugars or whatever, organics. And doing that, there is a release of the oxygen that was contained in the water in the form of atmospheric O2. In order to have a buildup of that, it's not enough, because there is the other reaction the other way, respiration or even just oxidation. So in order to get oxygen in the atmosphere, you need to bury some of the organics in the crust, and then to let some orphan in the atmosphere, some oxygen orphan. Okay, so it's not only linked with life, it's also linked with, let's say, geology or tectonics and sedimentation and stuff like that. It's very complicated. But we can make a very interesting calculation, because it's very easy to calculate the cost, the energy cost of this reaction. So we can ask the question, how efficient is it? What's the fraction of the sunlight that is used to do that? So we know the sun flux at the surface of the Earth, it's that in average. We know how much carbon is fixed by photosynthesis. It's this amount of tons of carbon per year. And we know that's the cost. We know the cost of this reaction. So if we make the calculation, it's 0.16% of the solar flux at the surface that is converted into chemical energy by life. It's huge. It's really huge. Think about all this light that's just fall into desert or whatever on our cities or whatever. It's a huge amount. It's a huge efficiency. And then life does not only do that. Life does other things. Like, for instance, chemoautotrophic life does not use light. So what does it do? Well, actually, indirectly, it's using the heat flux from the Earth. We know its value, and I will explain why in a minute. It's very difficult to use thermal heat as energy. It's a very high entropy energy. It's low quality energy. How can you use heat? How can you use heat coming from something that's about the same temperature as you are? Thermodynamically, if you make calculation, it's very, very difficult. So some people have tried to estimate the efficiency, and they say it's very difficult, but it's less than 10 to the minus 6. So it means that photosynthetic life fixes at least 10 million times more carbon than any primary producers on Earth. And you can compare that to this number. So actually, the reason for this inefficiency is that because life does not use directly the heat flux. What it uses is the gradient of temperature that you have in the soil, and the circulation of water that it produces, and the redox gradient that it produces. And this is by using these redox gradients that life can produce matter and do things. But actually, primary production by photosynthesis is going to produce 200, in average, 200 grams of carbon per year per square meter, while you would need 1 million a year to fix about 50 grams of carbon by using this gradient. And actually, that's not a surprise that although chemoautotrophy was known for a long time, it was really discovered in the depth of the Earth in the 70s, 80s, because it doesn't do much. There is no obvious sign of it. And actually, you can even say that in a world with a purely chemoautotrophic primary production, the organic sequestration would cause no significant biological effect on the global carbon cycle in the absence of photosynthesis. So it's very interesting because we can think of life in many environments. There are many habitable environments where you can have liquid water, organics, energy. For instance, you can live inside a planet with an isolation provided by an ice crust and some energy source that either comes from the inside of a big planet or because of tidal dissipation on a small satellites like Europa, Ganymede, or Callisto. But are we going to be able to see that from light years away if it doesn't do enough things? You see? So this is why actually the region in space where you can have both water and light at the same time is so interesting to us. So this is the justification for this so-called habitable zone, which has a very, very bad name because it has nothing to do with habitability. Habitability could be in many, many other places. But this is where we think it's possible. It's not obvious that there will be life. But we don't think that elsewhere than that, life would have the same kind of flag as it has on Earth. So I propose another name for the habitable zone because it has to do with liquid water at the surface and not really with habitability. It's not a question of habitability, but it's a very, very important region around stars. You missed the picture. You want it again?
Oh, yes.
Too late. I send you the slide. So there is usually a big discussion about habitability, and it's because usually, and this is what it means, it's where life, sorry for this, I'm not a master of English. It's where life can exist. But usually as astronomers and thinking about looking at exoplanets, it's more where we can find it. And actually, even if what you have in mind is where to find it, there is a big difference whether you think solar system, where you can go, dig, send a submarine or whatever, or this looks like science fiction, but this actually happened. It's amazing. This is how Curiosity landed on Mars. So I don't know what's the craziest of these two, but at least this one really happened. So it's very different when you think solar system or when you think extrasolar planets, when you will have an unresolved, low-resolution spectrum of a planet. It's really not the same. So this soft zone, this habitable zone, it's very important, and actually it has two boundaries. One that happens when you can no longer have liquid water because it's too hot and all your reservoir water is vaporized. And then when it's vaporized, it can be lost to space. This is what happened on Venus. Water gets photolyzed and the hydrogen is lost to space because it's very light. This can happen. It's not obvious that it will happen all the time. It depends on the gravity of the planet. It depends on the amount of water you have to lose. It depends on the activity of the star. For instance, it's very interesting that for the latest M dwarfs, so the smallest M dwarfs and the brown dwarfs, there is basically no extreme UV radiation or X-ray radiation. So you can have a steam atmosphere lasting there forever. But whatever. So this habitable zone, and there is this boundary, and then there is a boundary if you're too far. Well, whatever the amount of greenhouse gases you put in the atmosphere, you cannot get a surface temperature above the freezing point of water. So this is not actually completely theoretically true, because if you put a massive hydrogen envelope around an Earth, you can go as far as you want, because with the heat that comes from the inner Earth, if you have an isolation given by an hydrogen atmosphere that's not going to condense, whatever the temperature in the upper atmosphere, you can get 30 Kelvin, 300 Kelvin at the surface. It's theoretically possible. Does it exist? I don't know. But when we think habitable zone, we usually think more common greenhouse gases and mainly carbon dioxide, because this is based on the case of the Earth. So the inner part of the habitable zone, it's where actually you don't need any additional greenhouse gas. You don't just need water to be there. So imagine a big bowl of water, and if you have liquid water, it means that there is at least 6 millibar of water vapor in the atmosphere. It's the triple point vapor pressure. So by definition, if you have liquid water, you have at least 6 millibars, and a column of 6 millibars of water, it already has a significant greenhouse effect. So this inner part where water is self-sufficient, so you can get a climatic solution just with water. It's very, very sharp. So we are here and there. This is the temperature you get at the surface. This is due to something that is called the runaway greenhouse. It's the fact that, well, if you have let's say you have 100 degrees Celsius at the surface, it means that you would have, in average, 1 bar of water in the atmosphere. That's a huge greenhouse effect, but the cooling of the planet to space would be the same than with a much, much smaller surface temperature. So basically, it means that if you want to cool, if the planet needs to cool, it needs to radiate in the visible through the atmosphere, and this is why you get this really sharp change from about the temperature we have here to the melting point of silicates. So it's amazing. So Venus is not at this temperature because it doesn't have water vapor in this atmosphere. So CO2 is a less efficient greenhouse gas. But if you have one ocean of water available, then you will vaporize it about at this distance, and then you will get a surface temperature as high as that. So it's a very, very sharp region, and we are fairly close from the edge. Then you could say, okay, what happens if I take the Earth and I put, let's say, 20% farther away from the sun? You can do the mind experiment of that, or you can use a model to do that. If you do that, the Earth, it's simple, the Earth will freeze. It will get into a snowball Earth event. The temperature will go down to minus 60, in average, minus 60 degrees Celsius, and it will be frozen. So is that bad for the habitable zone? No, because now let's give time to the planet to react. There is the carbonate silicate cycle on Earth. So the Earth is producing CO2 into the atmosphere. It's releasing CO2 into the atmosphere. Right now, because there is liquid water, this CO2 precipitates into carbonates. It's dissolved into carbonic acid, reacts with sodium, calcium, magnesium, iron, produce carbonates. So CO2 is just passing through the atmosphere. But if your planet is frozen and you're cutting this loop, then CO2 will build up into the atmosphere. And in 1 million years, you will get 1 bar of CO2 in your Earth's atmosphere, and it will be warm. It will be warm again, and you will be back there, but with more CO2 in the atmosphere. So if you have 20% away from the sun, you will get maybe, I don't know, half a bar of CO2, something like that. And how far can you go like that? Well, about the distance of Mars, roughly. And that's a problem because if you think about Mars in the past, the sun was less bright than today, and it seems from our calculation that it was beyond this habitable zone. So we don't really understand how there was liquid water. Was this liquid water very stable or associated with bombardment, with big geological changes? We don't really understand. Of course, these are only models, so there is it seems that there was actually liquid water on Mars, so it's a very interesting question. But so the quantitative limits are not well known. The principles are understood, but the quantitative position of the limits of the habitable zone still needs to be refined, and observations in the future will help us, of course, to understand that better. But you can plot the habitable zone as a function of the type of star, and it's not just a question of luminosity. There is something that's very important, is the spectrum of the star, how red it is, because in the case of the sun, most of the luminosity is in the visible, and in the visible there are no molecular lines. If the star emits in the infrared, well, there are all the water bands, the CO2 bands, the CO bands, and so the planet is going to absorb much more. So with the same amount of energy that is intercepted by the planet, you can warm it much more efficiently. The albedo for the same planet, you take an Earth with an albedo of 0.3, 30% reflected to space, you put it here and it will reflect less than 10% to space, which would change the temperature a lot for the same irradiation. So this is what is illustrated here, but I will go past that. So for instance, for Kepler 186f, this is the amount of CO2 that you would need to have liquid water. So depending on the amount of nitrogen that is in the atmosphere. Why? Because the molecular nitrogen is not greenhouse gas, but it increases the greenhouse by the CO2 by pressure broadening of the lines. So if you have no nitrogen to do that, you will need something like 3 or 4 bars of CO2 to have this planet habitable. If there is plenty of nitrogen, you may need only less than 1 bar of CO2. But this is an M star, and there are problems with M stars, many problems. They are active, they flare, they have stellar winds, and because they are faint, you need to be very close to get enough light, and by doing that, you're subjected to very strong tides. And these tides end in synchronizing the rotation and the orbit and making the planet synchronized like this. And this is, of course, a big question for climates. How does climate react to that? There is, of course, the risk to lose all your volatiles on the night side where it's cold. So if you have a snowball event, like it happened on Earth in the past, how do you get your water back? That's a very big issue. Then when you have a synchronous rotation, you have no obliquity. And so you have very cold poles, and you may also lose your water and your volatiles on the very cold poles. That's something that is studied. Actually, what we found is that many different groups found that synchronization is not that much a problem. First, if you're in the outer part of the habitable zone, you already need a lot of CO2 in the atmosphere. And this thick atmosphere is actually a good way to redistribute, to recirculate the energy. So it's usually not a big issue. For an Earth-like planet, could be a problem, but what simulations show is that the day side, so you can see the day side is this one. Actually, this is the albedo. The day side is very, very cloudy, and the albedo increases a lot. So the planet is reflecting much more light, and actually it's interesting because it makes the habitable zone slightly closer to the star. And you can see it's very interesting that most of the energy that is radiated by the night side. This is the brightness temperature, and this is the night side. And you can see that the brightness temperature is around 300, while now it's the day side, and this day side is much, much colder seen in the infrared. It's because you have a lot of clouds and humidity very high in the atmosphere. The surface is, of course, hotter on the day side, but the thermal emission that an observer will see is actually less on the day side. Okay, I will maybe pass on this, but just to cite a work that has been done by Jérémy Lecomte, who is in our group in Bordeaux. He showed that actually atmospheres can prevent tidal synchronization. This was already known for Venus. Venus actually should be synchronized, but it has a slight rotation compared to the synchronicity, and it's due to the atmosphere. But nobody was able to quantify actually that. But using 3D atmosphere model, we were able to quantify actually the torque that is produced by the fact that the day side of the atmosphere is more dilated. And so actually there is a torque that tides produce on the atmosphere, and that's communicated to the planet. And this is, if you don't have any spin down by the atmosphere, this would be the limit. So you have the stellar mass and the distance. This would be the limit between non-synchronized and synchronized worlds. And you can see that, so the Earth is here, but very fast, most of habitable planet would be synchronized. But if you're adding this effect of the atmosphere, you can see that this limit could be here, for instance. So with most of the planets actually non-synchronized. Of course, in this kind of calculation, I will not give you much detail, but there is the problem of eccentric planets. So we are doing simulations of those, and it's very interesting. There are very different possibilities. I don't have much. How long do you give me? Because yes. 3 minutes? Okay. So I will end. So go. Yes, okay. Think of it as a movie. So I will finish by saying just a few slides that there was a debate in the past whether what should be the next instrument to study Earth-like planets around other stars. Should we observe them in the visible and try to see the oxygen feature? Should we observe them in the infrared and try to see the ozone band? Should we look for methane? Should we look for other species that life is able to produce? I think that now the community is more mature and thinks that actually we should not aim at biosignatures with the first missions, because what we need to understand first is the context. We need to understand what is a planetary atmosphere in general. We only have 8 planets in our system, and we see a lot of diversity. So we need to understand how atmosphere form, what's the diversity of them. We are going to find very odd things, I'm sure. And then on the specific target you're looking at, you need to have a lot of information. You need to know exactly what's the details of the composition. So whether you find information first in the visible, then in the infrared, then with this technique, it doesn't matter, because before having any kind of exobiological conclusion, you will need to know exactly the context. This is what was being done in the 70s with the Viking probes. They were sent there with an exobiology experiment, but with no context. And it was very difficult to give an interpretation of the results. It looked like something positive, like there was life doing something in the sample, but it's because there were other instruments saying, oh, there is no organic matter, oh, there are superoxides doing things that you would not expect from a sample on a desert on Earth. That's the results from the exobiology experiments were understood. So you really need the context, and it's better to get the context first rather than discuss for decades about is the methane that we've seen produced by alien cows or something else. So a few conclusions here is that attributing a spectral or chemical anomaly to the presence of life assuming that we can do that. This will require many observations at different wavelengths with very good signal-to-noise ratio and from different instruments. So it doesn't really matter which one is the first. And the detection of an anomaly is not the ultimate goal. It's the start. It's how does it resist to the analysis by the scientific community. So we don't need to detect things. We need to measure the abundance of things. We don't need to just say, oh, there is oxygen. There is oxygen on Mars. There is oxygen on Venus. How much oxygen there is and what else? We need to observe and study many different planets around many different stars, of course, to understand what are the processes controlling their diversity. And some things that you hear sometimes, NASA is good for that, to say maybe in 20 years or 30 years, we will detect life on another planet. But the success of this endeavor doesn't depend only on our technology, but on the actual distribution of life. We don't know if there will be life on the next planets, or if we have to dig all the galaxy to find. So we don't know. It doesn't depend only on us. It depends on the actual distribution of life. And so this is the way, maybe, in an optimistic view of what could be the detection of a biosignature. Or let's say there is a planet which is part of a big survey of many planets. This one is called TESH 42. And all these are observations that have been acquired by many instruments. So some observations, I don't know, in the visible, in the infrared, some observation just of the star to understand how the star works, or maybe of the other planets in the system. And at some point, and if we compare that with all the other planets we know, there's something we don't understand. There is an anomaly. There are two compounds that should not be there, and there is an anomaly. So the first effect, I think this planet would become very important. It will be a field of research in itself. And so there will be much more observations. Observation spread over time, over wavelengths. And it will take a lot of time to have a consensus from the community, whether it's explained by something else or it's probably life. So it will take, I think, a lot of time. And trying to find a shortcut from where we are to that would be counterproductive, I think. So if you would like to, if you think it's a very important goal in science, I think we should start by studying planets and atmospheres, and maybe this will come at the end of the way, but no shortcut to that, I think. And I will stop here.